So we're going to pick up where we left off and doing some example problems with the Doppler effects. We'll do 3, which is a short problem, even though I'm going to give you a big, lengthy context behind it. And then I want to go back and look at one of the derivations because there's a continuation of it that's going to be important for some of the problems. So number 3, we are trying to detect a planet that's beyond our solar system, an exoplanet. So imagine here is the Earth. We're here. We're observing. You don't have to write any of this down. I'll do the problem in a second. I just want to give you context. There's some distant star. And surrounding that star is a planet, Earth-sized planet we're hoping, and it's going around and around and around. Now, if you recall when we talked about gravity, they're both pulling on each other, so they're both orbiting a common center of mass. Let's say that center of mass is right there. So this star actually has an orbit that goes around and around like this. It's a really tiny motion. Okay, so the point is, if let's say the star is orbiting this way, when it's right here, it's moving towards us. In other words, there is going to be a red shift in the light we see when it's, a blue shift when it's moving towards us. And then when the star's orbit is right there, moving, remember it's going around and around, when it's moving tangentially that way, we will see a slight red shift. Now, how much shift we see depends on how fast this star is moving around and around. And since this is such a small planet, there's going to be a very tiny wobble, so we have to be able to detect that speed down to 10 meters per second, which is exceedingly small speed. So the question is, what percent shift in frequency, or wavelength, would we have to observe in order to detect that tiny speed, therefore to detect the presence of that planet that's causing that wobble in the first place? Okay, so what we want to understand is this speed would normally be given the symbol u in our equations. Okay, and the wave speed in this case is light, which would be normally given a symbol v. But what we want you to recognize in this situation is this value is tiny compared to the speed of light, right? The speed of light is, remember, 3 times 10 to the 8th meters per second. So in order to solve this problem, we don't have to use the first two equations for a Doppler shift because we can use an approximation where the speed of the object is tiny compared to the speed of the wave. In other words, we can use the equation, the last one we said, that says delta F equals F times V over C. Okay, and the V in this case is the speed of the object, and C is the speed of the wave, and in this case the speed of light. So what we're looking for is the percent shift. In other words, what we want to find is delta F over F. Okay, delta F is the actual shift, F is the original, so the percent is simply the ratio of the two, and that's simply V over C. So V is what we're trying to detect. Our instruments have to be sensitive to see that, so that's 10 meters per second divided by the speed of light. And hopefully by now you know that the speed of light is 3 times 10 to the 8th meters per second. So 3 times 10 to the 8th. So you can see it's a really small value. Now I'm going to multiply that by 100 to get at a percent. All right, and I'll do the math for you. It's pretty straightforward. We get 3.3 times 10 to the negative 6%. So we have to have instruments that are that sensitive to a blue shift or a red shift, depending on which way we're observing the star, that's that exquisitely small. And we're able to do that, so it's pretty cool. And in fact, our instruments are getting where we can detect this down to maybe even close to 1 meter per second. All right, to finish off, I want to go back to the very beginning of the derivations of the equations. Okay, so let me shift that back up maybe. And it's right here where we're looking at lambda. Okay, so when I was trying to do this derivation, I said, hey, if we have a stationary object, then there is a wavelength lambda. But if the object is moving to the right, then what we measure as the new wavelength from here to here, lambda prime, we said was equal to the original wavelength minus the speed of the object multiplied by the time that it releases waves, the period. And if it's heading towards you. If you're over here, that equation becomes lambda plus. Okay, so I want to do this in terms of take out the period part and just look at this shift in wavelength based on the speed of the wave versus the speed of the object. So we can do a fairly simple demonstration. So I'm going to start it again up here. So I've got lambda prime equals lambda, and I'm going to use the minus plus. Okay, again, minus for heading towards you, plus for away from you, period. Okay, now we know period is 1 over frequency, so this becomes lambda prime equals minus plus, oh, there should be a u here, sorry, u times 1 over f. Okay, so that's pretty straightforward. Now, if we look at our wave equation, what we're going to write here, let's remind ourselves that says our wave equation, that the speed of a wave, v, equals lambda f. Then I can do a substitution where I can say 1 over f. All right, if I solve for 1 over f there, that's going to be lambda over v. So this equation becomes lambda prime equals lambda, sorry, I messed up this part over here, minus plus u, which is the speed of it, times lambda over v. And if I move all the lambdas to the other side, okay, I'll do that one step, I get lambda prime minus lambda, so there's your shift, the difference in the two, divided by lambda equals u over v. The ratio of the two speeds. So that's really useful in some of the problems. Or again, u is the speed of the object moving and v is the speed of the wave. So there is essentially your Doppler shift in terms of wavelength instead of frequency.